So, first of all, I am grateful to all the participants who are either present physically in the hall or virtually. And along with that, their interest and special attention in the series on artificial intelligence is particularly appreciated. I am also grateful to Professor Khalid Mahmood Saab, who is President of the Pakistan Academy of Sciences. He is an eminent professor at University of Agriculture, Faisalabad, Professor Emeritus at present. And he joined virtually. He is with us now. Thank you very much, sir, for sparing time and for opening remarks for this. Now he is a very well decorated scientist. And another is Professor, already Government of Pakistan has awarded him this Tara Imtiaz and many other honors and awards. He served at various positions. And we are lucky to have him as the President of the Pakistan Academy of Sciences. Another respectable fellow who is present is also present virtually, Professor Ghulam Murtaza. He served Qaid University in various capacities as a professor and dean, Faculty of Natural Sciences, then Government College University, Lahore. And he served there as a professor emeritus, chair professor, and in various capacities. And he is also one of the fellows of the Pakistan Academy of Sciences, and Government of Pakistan has already awarded him also this Tara Imtiaz. So, mashallah, we are grateful to you, sir, for your interest in this series too, for your time. And thank you. From the students and the member of the Pakistan Academy of Sciences, Mazhab Khatak and Sikandar Saab and Osmanakram Saab. And you are particularly welcome, and hopefully we are going to start this lecture series. I am confident that we would manage few speakers in terms of 8 or 10 lectures through diversity areas in the field. First speaker, I am particularly grateful to Dr. Muhammad Osmanakram Saab, who is currently serving as an associate professor at College of Electrical and Mechanical Engineering, NUST. And he holds a PhD degree in computer engineering. Especially, he has a research area in medical image analysis. So, once the background of the series is through the interest of the President of the Pakistan Academy of Sciences, because you know artificial intelligence is quite hot area nowadays, and our respectable members and certain colleagues in Pakistan are working in this rich area. So the theme of the series is just to introduce and to share the knowledge and cross-fertilization of ideas in the field, so that we must be quite aware what one is doing, so that we can collaborate and coordinate in a better way. So this was the background, and especially I talked to Professor Dr. Muazzam Saab, Khatak Saab, that we should start a series of lectures on this topic, and he was very kind to take this job, and I am particularly grateful to him too. And first speaker, who is also eminent scientist, Dr. Muhammad Osmanakram. Sir, thank you very much, sir, for sparing time, and it is immense pleasure and honor for us to have you here as the first speaker of this series. So now I would hand over to President Pakistan Academy of Sciences, Professor Dr. Khalid Mahmood Saab, for the opening remarks. So, sir, to you.
Thank you, Dr. Saab. Bismillahirrahmanirrahim. Dear all present participants, professors, it's a pleasure to have you here in the Academy of Sciences. for this series of lectures arranged by Dr. Sabar Hayat. You know, PAS has been regularly organizing webinars, symposia, and lectures from prominent scientists and experts for the benefit of fellows and the students. In addition to individual lectures, PAS arranged a series of international webinars on various aspects of agriculture last year. Dr. Iqrar Khan was the host. This year, Dr. Sabar Hayat is arranging a series of lectures on artificial intelligence and Internet Things at PAS in collaboration with Qaeda University. This series will continue till June, and approximately 8 to 10 lectures almost bi-weekly by the prominent experts from academia and industry will be taking place. You know that AI is becoming an important player in our life. It has formed its initial uses in industry, healthcare, education, agriculture, and most recently in services. Machines are being developed who are doing jobs as human beings. So it becomes imperative that researchers and students have a clear vision of artificial intelligence. This series will cover various aspects of AI and its development and uses and benefits. I hope that at the end of this lecture series, we will have a better understanding of artificial intelligence and have more people coming in research in AI and have new ideas, new initiatives to develop new machines and models. Today's lecture on AI application is in healthcare sector. Dr. Osmanakram, as has already been mentioned by Dr. Sabar Hayat, is an associate professor in NUST who holds a degree of PhD in computer engineering with specialization in medical image analysis. He will deliver a lecture on AI and deep learning on ophthalmology. I am thankful to Dr. Osmanakram for accepting our invitation and sparing time for this lecture. I hope this lecture will be quite useful and beneficial to all the listeners. I thank you all. Thank you and God bless you.
And in addition to that, I have noticed that there are certain participants who are participating virtually. And I have apologized not mentioning about them because at that time I do not know. So I am also grateful for all of them to spare the time for this lecture series. So thank you very much for all. Now, before starting, I would like to hand over the dice to Dr. Mazum Khattak, who may act as a moderator of this lecture series, and to introduce the first speaker, Dr. Muhammad Osmanakram, sir. Thank you very much.
Dr. Osmanakram to share his thoughts on artificial intelligence and also share the opportunity in which we can collaborate with his research lab. As I mentioned, Dr. Muhammad Osmanakram is a renowned scientist, and recently he has been awarded gold medal by Pakistan Academy of Sciences in the category of scientists under 40 years of age. He is also running a company and that is also contributing toward different diseases by some equipment as well as He will share his knowledge about the industry and academia where we have opportunities to collaborate and as well as to explore new ventures in the field of artificial intelligence and machine learning. So now I would like to invite Dr. Muhammad Osmanakram to please come on stage and give his address and speech about artificial intelligence. Thank you.
Assalamu alaikum. First of all, I am very thankful to Pakistan Academy of Sciences for giving me this opportunity to share the R&D work which we are doing at NUST and in our company as well. So generally, I will be talking about specifically what we have done in the area of ophthalmology with respect to AI and deep learning. I am heading a research group in NUST, that is a Biomedical Image and Signal Analysis Research Group, BioMESA. And there we are working on different healthcare related problems to solve them with the help of technology. And mainly, one of the work which we have done is in the area of ophthalmology. So in this whole talk, I will specifically talk about what we have done in the ophthalmology, but I'm totally open with respect to any kind of questions, remarks, or comments which you can ask at the end of this lecture, like what we are doing with respect to AI and what are the future aspects of AI in healthcare specifically. So, and another thing is like you are more than welcome to visit our lab, BioMESA, and its web page as well, where we can have different kind of collaborations. So, like before going into the actual technical details, I just want to cover some of the numbers just to show like what kind of social impact we can have with AI if we are working in the area of biomedical in healthcare. So especially talking about ophthalmology, like we have 285 million visually impaired persons across the globe, and out of them 19 million are the children, and 90% of them they belong to the low income countries like Pakistan and this Asia region. And one of the things is like 80% of this blindness or visually impaired issues are curable if they are detected and treated on time. So like if 80% are curable, so why the numbers are so high? So one of the reason is the doctor to patient ratio. Like if we specifically talk about Pakistan, we have 1.8 million glaucoma patients and around 480 people develop some kind of eye disease on daily basis in Pakistan. And 90% of them, they belong to the rural areas. So now government does provide different kind of infrastructure like basic health units, but those basic health units, they do not have the specialized equipment or they do not have the specialized doctors with them. So like even if the basic setup is there, but the technology or the specialist is not present over there, which can be used to treat these patients. And as a drawback, what happens, like all these 90% from the rural areas, they come to the urban area, and we have, like, we all know the situation in hospitals in major cities of Pakistan. So one of the possibilities that we can use the technology to lower the burden on the hospitals in the main cities, and we can provide virtual or online access or any technology-driven access to these patients. So before going again into the technical details, as we are talking about the ophthalmology, so I just briefly cover like what we are talking about. We all know about the human eye, and once we dig into the eye from the pupil, we have retina at the back of the eye. And the retina is responsible for the main vision, like we all know about rods and cones. Retina is the region which is rich of rods and cones, and those rods and cones are responsible for the day and night vision, for the color vision, and everything which we see. We have different kind of imaging technologies available, which we use to acquire these to diagnose, to acquire these fundus images that are fundus cameras, and then we have another relatively latest imaging technologies which are known as optical coherence tomography, which gives you in-depth visualization of retinal layers. So the ophthalmologist or the eye doctors, they use these imaging technologies to diagnose different kind of abnormalities which are present in human retina, which are actually responsible for different kind of eye abnormalities. So whenever we are going to do, or we are going to develop any technological spot for the eye disease, we have to deal with these images, either the optical coherence tomography images or the fundus images. So the main diseases which we have, ocular disease, which are most common, out of them, we have major part comes from the retinal disease. So just the retina is responsible of major chunk of blindness which is present right now. So again, before going towards the technical part, I just briefly, like I have some short videos with me, which will tell like what each abnormality is and how they develop. So first is macular edema.
Diabetic macular edema, or DME, develops as a complication of diabetes and is a leading cause of vision loss among working adults. Anyone with type 1 or type 2 diabetes is at risk. DME involves the retina, the tissue at the back of the eye that receives and processes what you see, and the macula, which is a small part of the retina critical for seeing clearly. DME occurs when blood vessels leak fluid into the retina and macula, causing edema.
So due to diabetes, what happens, like the blood vessels, they get weaker with the age, and then due to the bleeding, we have different kind of hemorrhages or other abnormalities which cause different kind of vision loss. Another major retinal disease is glaucoma, जिसको हम काला मोतिया भी कह रहे होते हैं, ठीक है? तो glaucoma.
In the healthy eye, a clear liquid called aqueous humor circulates inside the front portion of the eye. To maintain a constant healthy eye pressure, your eye continually produces a small amount of aqueous humor, and an equal amount of this fluid flows out of the eye through a microscopic drain called the trabecular meshwork in the drainage angle. If you have glaucoma, the aqueous humor does not flow through the drainage angle properly. Fluid pressure in the eye increases, and this extra force presses on the optic nerve in the back of the eye, causing damage to the nerve fibers.
So the optic nerve are the region which are actually connecting the eye to the brain. So if any damage happens to the optic nerve, so the brain would not get the actual signals and the eye will not work in a proper way. And in glaucoma, generally we have high intraocular pressure which cause these kind of disorders. Another is age-related macular degeneration, like the people above 55 or 60 years of age, they generally have AMD.
Age-related macular degeneration, AMD, is a disease that causes progressive damage to the macula, a central region of the retina. The retina is the light-receiving nerve layer located in the back of the eye. As the eye ages, debris from the RPE cell layer and surrounding tissues accumulates above and within the Bruch's membrane. The debris form deposits called drusen. The presence of drusen is usually the first sign of early dry AMD.
So all these abnormalities, they are being diagnosed with the help of imaging technologies. Like I have already talked about the fundus images and optical coherence tomography images. So the fundus and OCTs are the non-invasive way of acquiring human retina. Whereas in FFA, fundus fluorescein angiography, the doctor first injects some kind of dye inside the vein, and then they acquire a series of eye images to see where the leakage is there in the eye and where the blood vessels are not functioning properly. So generally, when we talk about AI and we want to develop some kind of decision support system, so we should go for non-invasive way in which there is no need of clinical kind of investigations. So that's why the fundus and OCTs are the most widely used imaging technologies for computer-aided diagnostic systems. So again, for all this, we need specialized cameras and we do need ophthalmologists. And why I am talking about ophthalmologists again and again, we have only one ophthalmologist against 0.1 million patients. So like the WHO that says we should have at least one physician against 1200 to 1500 patients. So you can well imagine how that doctor to patient ratio, we are quite below than the minimum threshold, especially when we talk about specialists. Because eye is a kind of area where normal medical doctor will not work. You need specialist doctor to deal with eye disease. And this is not the case only with Pakistan. The developed countries like America or Europe, they are facing the same kind of challenges. So keeping this thing in mind, first time in its whole history, FDA, America, they have approved the first AI-based diagnostic system, and that was also for the retinopathy, that is one of the eye diseases. So it means FDA have also realized this thing, like AI should be there to help the specialists, and especially in healthcare. And as a first case, they have taken the retinopathy. So that's kind of motivation which we have, like we should work in AI to solve different kind of healthcare problems, especially the ophthalmology, which is one of the most area where we should apply AI. So keeping all this in mind, like 6 or 7 years back, we started working in ophthalmology area, and we over the time we developed one system in which we have a number of institutes in Pakistan who are collaborating in this venture, and we developed ALBASR, which is a standardized web-based electronic medical record system. That's a traditional EMR, like web-based EMR. But the beauty is like it has built-in decision support system which are based on AI and image processing and deep learning techniques. And it has also the telemedicine part, which like make it suitable to be used in any rural area. So like it has EMR, which is web-based solution, then it has telemedicine component, and mainly, which I will be talking today, is the retrovision, where we have used AI, deep learning, and image processing algorithms to solve different retinal diseases. So I'll just share a short video about ALBASR, and then we'll go into the technical details.
Introducing ALBASR. It is a comprehensive medical record system that is specially designed for use in ophthalmology. It provides an easy-to-use interface for patient record storage and retrieval. Patient encounters and entire visit history is summarized in a singular view, enabling a consultant to determine patient state efficiently. It works in an integrated environment with the hospital's investigation room, keeping track of all the investigation data. It brings to an immediate reach of a consultant all investigations that are being carried out during a treatment, such as, most commonly, FFA, HES chart, slit lamp, BKG, OCT, fundus, and many other investigation types. Most importantly, ALBASR provides set of intelligent analysis of the eye, integrated to its core, such as diabetic retinopathy and glaucoma analysis, which assist a consultant in a correct diagnosis of the condition by identifying, with impressive accuracy, the severity of the problem. ALBASR incorporates findings in fundus images analysis and correlates them with the findings in OCT analysis to intelligently generate an automated report, highlighting major parameters that help immensely in a correct diagnosis. The ability of ALBASR to perform such accurate analysis independently also qualifies it to be used in telemedicine and telescreening systems, and so it provides provision to securely refer cases to consultants that are a part of the system, but are geographically distant.
Okay, so we highlighted one gap in the area of ophthalmology, and we do have some expertise in AI and image processing. So we just jump into that area, and again, over the period of 6 to 7 years, we were able to develop this system. So it's a complete suite which have multiple kind of options available. So now, what kind of AI is there? What kind of algorithms are there? What we find out, like in different kind of abnormalities, we are not from the medical area, we are not from healthcare, we are purely from engineering background. So initially, what we did, we understand the whole problem. We understand what kind of changes are there which appear in different kind of imaging technologies and what actually ophthalmologists look for. So if we can understand that thing and we can mimic ophthalmologists into some kind of algorithm, so they should be able to identify all those kind of abnormalities. So keeping all the changes in mind, which appears in fundus images and OCT images, we develop a complete framework which is based on image processing, AI, and deep learning algorithms, and it's a single framework which is handling the both kind of imaging technologies of fundus images as well as OCT images. So that single framework that consists of, like, as we are dealing with the images, so we have to do some kind of basic image processing as well before going into the AI or before training the system. So it does have the modules which does some kind of analysis on these images, and then those kind of findings or things are fed to machine learning algorithms, machine learning models, or the deep learning models. And once they are trained, so we combine all these findings and eventually it diagnoses different severity levels. And another thing is, like, once we are developing the solution and we want that it should be used by the doctors, so we have to provide them something which they are used to. Like, they are not used to this thing, like this patient has this disease, because they are good to identify that thing, but they want some kind of insight, like why this patient has this disease or what kind of changes are there. So we couple that AI again with the graphics kind of things, with the 3D modeling, and we develop the complete 3D model of human retina. So now the doctors can play around with this 3D model along with the diagnosis, and they can find out like where the changes are being happening and what are the major causes which are leading to a specific kind of diagnosis or disorder. So again, like, it's the initial steps are the image processing. We did identify like what kind of challenges are there. So we developed different algorithms which are capable to highlight different layers of retina. Like, we have 9 to 10 different layers in retina, human retina, and each layer corresponds to different kind of abnormalities. So if we want to develop an algorithm that should initially highlight these layers. So we have developed in-house structure tensor based algorithms which are capable of highlighting all these layers, and we complement this thing with graph theory and dynamic programming so that it has optimal kind of implementation, and because there are a number of layers which we want to highlight, and if we want to have it as a commercial software that should run like how the doctors are working. They should not wait for 5 to 10 minutes and the results are processing and they are waiting for the results. So we complement it with the dynamic programming, and eventually we have a complete graph search which highlights all these layers, and then once the layers are highlighted, all kind of exceptions like outliers and noise, they are removed from these layers. And this was the part which is actually belong to the image processing or signal processing. But once that is done, now we have the AI part, because we want to train a system which can identify like what these changes actually refer to. So what we did, we developed a complete RAG network, retina analysis and grading network, RAGNet, in which we utilize the strength of deep learning, which have a capability of, like, if we have sufficient enough data, it has the capability to learn the changes. So we have 150,000 macular scans, which were used to train the original RAGNet. Now it has the capability to see all kind of changes which are being which are appearing in the layers, and once it has highlighted all those kind of, it has run all those changes which are appearing in the layers. So now it can highlight those to the doctor, and it can also diagnose what kind of changes, what specific disease is there. And moving forward towards the glaucoma, we further utilize the same RAGNet, and we tweak with this thing, like there are different kind of abnormalities. So it's not kind of a black box, like you use deep learning or AI as a black box, you just feed in the images and it just tell you what the abnormality is. We have to identify what parameters are eventually leading to that specific kind of change. So what we did, we designed a complete model which have inherent capability of highlighting the retinal boundaries or the lesions. With those retinal boundaries or lesions, it highlights the changes within the boundaries, and then using those features or attributes, it can identify what level of glaucoma it has. And then comes the the beauty of the thing, like the brain of all this framework. It's not just like we are solving one problem, because the issue with AI, machine learning or deep learning is that like you have trained it and it is doing one thing perfectly. But what if now you want to use the same thing for another kind of diagnosis? So will you go back and redo the whole thing from the scratch? And that's the main thing which generally people are using. But from now onwards and the things in last couple of years, there are concepts of incremental learning, there are concepts of continuous learning, because we do not want to go back and then again train it from the scratch, because that has time complexities, that has the computational complexities, that also have the parameter complexities itself. So what we want, another complexity is like we don't have enough data for every disease. So what we did, like we have we were lucky enough, like we have collaboration with AFIO, Armed Forces Institute of Ophthalmology in Rawalpindi. We collected, like I have also already mentioned, we have around 150,000 retina scans. So we collected all those scans. We trained a basic model on that. Now that model is capable of, now it knows how a retina looks like, or how the changes are there in the retina. So now if we have even small set of data for a specific kind of disease, we can just incrementally run the same model. So the beauty is, like, if we have, let's say, a batch for a specific kind of disease, we trained our AI model like general cross entropy based law, using cross entropy based laws, and now it has the capability of identifying, let's say, two kind of abnormalities. Then we have another abnormality, and we have a subset of images for that abnormality as well. So now we have a weighted kind of loss function, which have all the things which it has already run from the cross entropy. It has a mutual distillation in which it can incrementally run without forgetting what the network already knows. So the thing is, we do not want to retrain the whole network. So here, gradually, it's capable of knowing different level of abnormalities. Another thing is, like, this is one kind of imaging that is optical coherence tomography, like, or you can say for COVID, we have chest X-rays, we have CT, we have MRIs as well. So we have a large set of chest X-rays, but we do not have a large set of CT or MRIs. So if we have a trained network on COVID, for example, for X-rays, and now we have some small subset of CT or MRI, so does that network have the capability to learn, to take the already existing knowledge and then learn about the changes which are also being highlighted in CT? So we did this, like I just take the COVID case as an example, but we did this for eye, where we initially does this thing for OCT, and then we incorporate OCT with fundus, and now it has a complete learning of OCT and fundus. And in the inference stage, we just pass the data of any patient which is coming in, and it can tell you a series of abnormalities with it. And it's like kind of incrementing day by day, like what we are continuously working with the doctor, and the disease which they want to include, we just want a small subset of that data, and we are just incrementally continuously running the models. And then it comes to the like modeling part. Once we have all these layers as well, and we also want to highlight visually the retina to the doctor. So what we did, we combined all the layers. We generated 3D surfaces for each layer, and we also applied modeling to have actual, to highlight the actual variations within those layers. Like we have different kind of models, with reflection models, which we applied on this. And now we have a 3D, proper 3D representation of each retinal surface. And we morph fundus images on the retinal surface so that they also know like what kind of changes are happening on the fundus as well as within the layers. So this gives us the complete 3D surface. So now we have one-to-one mapping between the fundus and the OCT, and they are linked together, like what kind, like if some kind of change is being highlighted here, so how much thickness or depth is in the surface, and we have a 3D surface which they can play around. And again, with the help of AFIO, we did a complete clinical studies as well for this. When we do research in the lab or in the academia, we generally use a control group of images or this set, and we generally develop the we just want to like have a proof of concept that these algorithms actually work. Like all the framework which I have shown, like we develop that in the lab. Like, but once we have done that, we have to test it in actual environment as well. So for that, what we did in AFIO, we selected 4 ophthalmologists, and they blindly tested all the algorithms on different subjects. So what was happening, like a patient was coming to OCT room, and his or her scan was taken, and that scan was given to the server as well as to different doctors. So in the end, we were comparing their results, and we were getting very low false positives for this. And this is an ongoing process, because we are not saying that AI will replace the doctors, but they will surely assist them. And all those doctors will be replaced by the doctors which are AI, like they have the knowledge of AI. But AI is not going to like kind of replace the doctors. But we should have AI at the back end to support all the diagnostics. So now we can say, like, we have a single framework which has the capability to diagnose different retinal diseases irrespective of scan quality, scan acquisition, machinery, and the pathology. So we do have the images from spectralysis, we do have the images from top cone, from the eyes, because we just want to have a single framework which has the capability of incorporating all these kind of variations which does occur when we go from one vendor to another vendor. So again, the doctor would not like, if we say if you have to retrain the whole model. So what we did as academicians or being in the university, we make all these datasets available, publicly available. You can download it from our website, research group website, and we have a detailed, like, we were lucky enough to have multiple organizations on board. We started with NUST, EME, and Case Care, and Sari sitting here, Dr. Shafat Bazaz was part of this project as well. And we got initial seed funding from Ignite, but later on we moved towards our company, that is Diagnostics, and now we have a proper commercial software which we are like, which is in commercialization phase with the help of Diagnostics. And one of the success stories on all the effort which we have done, all the lab research or work which we did, and then we did some work with AFIO. We were approached by Ocular Imaging Research and Reading Research Center, OIRRC, that is a California-based company, and they have ophthalmology from Stanford. And now we convert the ALBASR into a complete AI-based ophthalmology grader, which is a cloud-based expandable solution. It has a modular structure to incorporate any kind of requirement. And one of the major things which it has is the quality assessment. Last year, there was a news in April 2020, like Google introduced the system with help by their study in India, which was on diabetic retinopathy. And once they deployed that system into Thailand, that failed miserably. Now, the question wasn't about the models which they developed. The question was about the quality of the operators which were present in Thailand. They were not of that expertise which actually the Google had, or the images they used. They actually didn't consider that level of variation into their model. Like there can be intra-operator variance as well, or inter-operator variance as well. Like the doctors which is quite expert in using the machinery, and then we have optometrists, they are collecting the images. So what OIRC asked us for, they knew this Google story, and they are also in USA. So they want, before going into the grading thing, they want in detail AI-based quality analysis. So it's kind of AI quality officer. So they do have quality officer which initially check the images with respect to different perspectives. Like a photographer will look at the image from a different perspective. A doctor will look at the image from a different perspective. Like we will look at this image with respect to exposure, with respect to focus, and the things are clear or not. Whereas doctor will look at it like what kind of abnormalities they are looking for. Either they are visible or not. Even it's underexposed, but still if there are abnormalities which are present, so it's gradable. So we did develop a complete QC module in this, and then we have detailed fundus image analysis, which is capable of, right now it's capable of finding 30 plus findings for a single OCT, a single fundus image. And then we have, like I was talking about, we have incremental learning mechanism in this, and we are keep adding the different kind of findings which they want from this model. And of course, it has different role-based success as well. So this is a complete solution which is actually originated from ALBASR, and now it's being used as a AI-based ophthalmology grader. Another thing, like where the AI or deep learning is going for, and where we are actually working with respect to our recent research. Another thing in medical or healthcare is, again, the doctor, they are least bothered with the diagnosis, what abnormality it has. Of course, we need those if we are using the algorithms as a computer-aided diagnostic systems, which are being used some remote areas, and you just want to prioritize the patient. But once we are giving a tool to the doctors, they actually want to see what kind of things were there which actually leads to this diagnosis. So another thing is detailed medical report generation. So with the help of deep learning algorithms as well as the NLP, natural language processing, now we are working on how to use image processing, deep learning, and natural processing to generate a complete report, like what kind of vision attributes are there, and then what kind of natural language tags are there, and we should generate a complete report. So we are already working for CXRs, but right now we are in the phase of collecting data for ophthalmology, and this is one of the areas where the research in healthcare is going forward. Like they are after generating complete medical reports. Another thing is explainable AI. Again, we do not want to use deep learning as a black box, or we do not want to use AI as a black box, like it's doing some kind of magic and it's just saying us like, this is the output. We actually want what kind of knowledge was there in the network which actually lead towards some kind of findings. So if it's saying like it's diabetic retinopathy, so what are the actual things which leads towards the diabetic retinopathy? So we are also working on this, like right now we have different kind of tags, but we are working on this as well to generate these complete knowledge graphs for explainable AI. Another thing what we did, like we were working on this ophthalmology area, and once we had that interaction with the doctors, so there were different kind of needs or different kind of issues which they were highlighting, and they want the solutions, a technology-based solutions for that. One of that was like when we talk about the rural areas, the excess of rural areas are twofold. Either we develop some kind of telemedicine system like with the 4G and all kind of internet accessibility, we can have telemedicine kind of scenario where we can remotely see the patient in the rural areas. But the issue is like no specialized equipment is there. So what you will do just by looking at the patient, like it's not with respect to simple like a simple assessment of a patient. You have to look at the retina, or you have to look at the fundus to find out like what kind of changes are there. So another solution is mobile vans, like Shifa, I trust they do this thing quite oftenly. Like they have different kind of visits to the rural areas where their doctors, along with the equipment, they have different kind of remote camps, and then they assess the patient there. But again, this is a like kind of temporary solution. So one of the thing which came up from AFI, like they want a portable kind of acquisition of retina and analysis of retina. So what we did, we made a gadget which we can place along with the camera, and using the lens which they were using in the fundus camera, we can acquire we can look at the fundus of human eye by simply placing a lens across the camera. So again, we were into the image analysis of AI. So we thought of that if we are getting this data, so can we do some kind of analysis on it? Of course, it's not of that quality. So what we did, we again used the deep learning based localization modules where it localized this iris from all the frames, and then it stitches it back and give it to the network, and it actually tries to diagnose like what kind of changes are there. So we did file patent for this, and we also got one in the Korea as well, and one in Pakistan is under process. So another thing, again, why all these things are there? Because we were directly in contact with the doctors. We were not sitting in the lab. Like once we are sitting in the lab, we can only do what's available, what's publicly available, or what's we have over the internet. So like we were sitting with the doctors, so there were huge number of possibilities which were there, and they were giving us different kind of problems, and we want to solve them. One of them again was the strabismus, bangappan jisko hum kehte hain. So 1 out of 36 children, they have strabismus. So in strabismus, again, this is twofold. One is just cosmetic issue, like both eyes are looking at different direction, but you do not have any kind of vision problem. But this is one kind of abnormality as well, where the patient would not be seeing the objects or things at the place where they are actually, like if this is here, so a person with strabismus might be looking like seeing this thing placed here. So what we did, like they told us like it's quite manual process, and before going into the surgery, they have to make a graph on the paper where they have to do the complete assessment of the patient with the strabismus, and the whole process actually took around 25 to 30 minutes, and then they go for the surgery where they actually do like what kind of muscles they have to stretch or relax. So what we did, we developed a complete system for that, which have that testing equipment where they see like where the actual patient is looking at, and it has a like rule-based, AI-based software where they just mark on the software, and once the patient is done, they just click on a click of button, the whole report is generated. And this system is being used at AFI or new hospital, like all these kind of hospitals. Like if you go in any of these eye hospitals, our system is there. And already 5,000 patients have been tested on this. So this whole report is generated automatically, and it have a rule-based AI behind it where it actually tells where the fixation point, like how much angle of deviation is there, and because based on these parameters, now they will tweak this during the surgery. And one last thing, again, for all those who are interested in gaming or virtual reality, another abnormality is amblyopia, which is lazy eye, and it's quite common in the children, in which like one eye is strong and other eye is very weak. So what a child would do, he will only is like the brain will try to look at from only that eye which is working, and with the time that lazy eye that will like it's completely out of order. So you cannot use that eye. So what doctor does, they place patching on strong eye and they force the kid to look at from the lazy eye or from the weak eye. So with this therapy, they try to like enforce the brain to look through that weak eye. So one kind of thing is being done with the help of VR, which is where we can have AI enabled games where they can like blur out the vision from the for the strong eye and they just leave the vision for the weak eye. And with the time, and why it's AI assisted, because it has to see like where the child is looking at and how much strength it has, like for how much time it's looking at from that specific eye. So with the help of AI assisted, VR therapy, we are now developing this kind of gadget where we can use the games for the therapy of amblyopia. And here we are working with University of Pittsburgh, where they are helping us in developing those kind of, like what kind of scenarios should be there to motivate a child to play that specific game. And it's relatively like it has more impact than the patching, because patching is kind of passive scenario. You have placed a patch, but you are not making sure that the child is actually looking through that weak eye. But once it's playing the game and through AI, you are actually looking at whether it has some kind of interaction with the game or not. So you are actually forcing that kid like to use that weak eye. So it has that, of course, VR has some kind of that cons as well, like they have dizziness, and of course the headset they have different kind of weight. So initially we are going for Google Cardboard, but Oculus Rift, they are being used for these kind of therapies, but they are quite expensive as well. So right now we are going for Google Cardboard to have a low cost, non-surgical, non-invasive treatment for this. So in general, what we aim for at the initial stage, like 80% of blindness is curable. So if we know the technology and if we have the access to ICT, information and communication technology, and if we have AI tools with us, so why not to address this 80% people where we can play our part to address or to solve some of the cases where we can avoid permanent blindness. So with this, I think, thank you. So any kind of questions?
For the very interesting lecture. So any question from the audience?
So why didn't you use that, sir? Why didn't you use the black box? Why did not use the black box?
Not use.
Use the black box.
Why we use the black box?
Why you did not use the black?
Yeah. So that's the thing which I was telling you, like if whenever we start anything with respect to research, we generally want some kind of initial results. So in that scenario, we want some quick implementations. So we go for black box kind of things. Like we do have the models. If we have the data, we just want to be the first one to get the best results. So like there it makes sense. Like we use it as a black box and we go for a quick kind of solution. But once you are going to provide a solution to the end user, like they are spending the money and they are going to use, they are going to trust on this system. So they should know like what kind of findings, like what kind of working it's doing and why it's saying like if it has diabetic retinopathy, so why it's there? Because that's not the way the doctors work. They have the clinical findings, they have different kind of assessments, and then they go towards some kind of diagnosis. So eventually, if we want doctors to trust on AI, explainable AI is the solution. Like that black box kind of thing will not work. And we have faced that difficulty like since 2014-15 we are working on this. So now it's going to be like doctors are accepting this thing. Otherwise the same question was there, like why it's saying this, why I should trust on it.
That's answer my question. Thank you.
So it's like we have a complete framework. So it does have segmentation modules. It have a classification as well as localization modules. So whenever we are going for segmentation, we at the very basic we have encoder decoder kind of network. But whenever we work for some kind of medical scenarios where some findings or lesions are going to contribute in specific kind of output, so we should have lesion aware encoder decoder. It's not kind of a simple encoder decoder which is going to work for segmentation. And similarly for localization as well as for classification, we have lesion aware classifiers.
Thank you, Yusuf, for the nice lecture. I was just curious about that, which specific outcome of your graphs, in sense of those graphs you were showing, were helping the doctors in order to identify the different stages of progression of glaucoma. So this is my first part of the question. The second was a bit informative, that why FDA has just approved that for retinopathy and not other AMD and other things. While third part is that, can you, what's your comment on that in a country where we are lacking a huge amount of data, so what we are doing in spite of AI, we are collecting the data first. And the thing which you are showing is the collection of the transcription data that is already available in first world countries. Back in 2003, I was doing that. So that is a huge lacking in our country. So how can we manage on that? These are three important elements which I highlighted.
Thank you so much. The first thing is like, as in the first question they asked for, like why we didn't use it as a black box. So the same kind of thing motivated us for the layer based analysis, like the graph search. All the graph search and the dynamic programming, we are using that for the extraction of layers. Like if we can go 30th को आप कीजिएगा. So it's quite easy. I can have a pool of scans which have glaucoma and which do not have the glaucoma, and I can train a network which can just tell like it's healthy or it has some kind of glaucoma. So, but what we studied, like there are certain kind of variation which are appearing in these layers, like these 10 to 11 layers of retina. So each variation that leads to different kind of abnormality or different kind of severity. So one of that region is that GCC region, the ganglion cell. Like in glaucoma, generally the ganglion cells, they vary with the passage of time, and the doctors do have a progressive analysis how these variations are being done. So we're motivated from that, and we use the graph theory to extract these layers first. We have all 11 layers with us. But for glaucoma, like once we are doing it for glaucoma, we are interested in GCC, IPL, this kind of region, the retinal nerve fiber layer and the GCC region. And once we do it for macular and for, let's say, diabetic macular edema or age-related macular degeneration, we are normally looking for RPE layer. And there are different kind of drusen which make some changes over there. So we have the expertise of image analysis as well as all those kind of implementation of like vision, which have these dynamic programming and or graph-based implementation of images. So instead of just jumping into the AI or deep learning, we actually utilizes that, and that was the thing which motivated the doctors. Actually, they were amazed by looking at like how here we are showing it in terms of a picture, but when I was showing you the ALBASR video, in that we actually quantize these values. We do have the numbers with. They actually look at those numbers, and they actually rate it like, okay, it's early glaucoma or it's advanced glaucomas. So that's why we begin into the, we went for graph for the layers. And the other one was like for retinopathy, diabetic retinopathy is one of the leading cause of blindness, because like diabetic is one of the leading disease which we have across the globe, and diabetic patient would have some kind of DR. So that's why that was one of the most widely used retinal abnormality, and the data was there for that. So because of the data and also the numbers for the DR were quite high, even the, like once Google jump into this kind of thing, so they actually aim for DR. And FDA, why FDA approved the DR? Again, the Professor Abramov, they are one of the leading in this area, and again, they were doing some research first, and once they have developed the system, that was again for the DR, so they filed, they sent it for FDA approval. And the doctors and the AI-based system both are in 80 to 85% of accuracy range. So their system is around 83, 84%. Actual ophthalmologists also have 85% of accuracy. So the only reason was like it is one of the most widely disease for retina. And the third one was, yeah, for, again, what we say, like we do listen this thing, like we do not have the data in Pakistan, first of all, like all the labs, like we have different centers now, AI, robotics, and cybersecurity centers in Pakistan, and they have different kind of labs who are working in medical scenario. So what they are generally they are doing, or what we also did in the past, like we use the data which are publicly available, which are benchmark data sets, and they are publicly online available. But the thing which made possible for us to achieve all these kind of things, that was the direct interaction with the doctors, with the hospital. We showed some initial results to them, and then we didn't impose anything from our side. Everything was driven from their side, and we give this kind of confidence to them. Like if they are saying something, so we have the capability to incorporate that thing with the help of all the technology. So that is one, like data is there, but you have to like give them some kind of confidence why they should share their data with us. We have proper IRBs, we have proper clearances, and then we got the data. And once we got the data, then again taking the 4 ophthalmologists or 5 ophthalmologists on board who will like validate your results, and they grading their own data, it's not quite easy, like until unless you have a proper like link with them. And another thing is, without their knowledge, like it's just kind of a lab work. So if we really want to impact something, we have to take them on board.
Sir, my question is regarding transfer learning. As you mentioned that we have trained our base model using fundus images, and we can also extend it to detect corona disease. And is it possible, sir, to extend a model that is trained on different modality of images, that is scan images, and we extend it on X-rays images?
Yes, of course. Like what in transfer learning you are doing, like we are generally using the models which are trained on ImageNet, and ImageNet have daily life images. They have nothing to do with the medical data, but still we are using transfer learning to take some learning from the daily life images, and we are expecting that they should work for the X-rays, for OCTs, for MRIs. Of course, they are working because that's the inherent capability of deep learning. Like it's not something which we are doing. That's like with the computation or with the inherent capability of DL, that transfer learning is working. But that's not the approach. Like if that transfer learning is working because that has the backing of that strong ImageNet data set, and that has the backing of that variation which is in the ImageNet data set. So specifically for CXR, we have quite large data sets right now. We have CXR 14, we have NIH data set which are publicly available, we have MIMIC data set which have 300,000 plus data. So why not go for that? And of course we do need resources, like that's the major limitation. Like if you do not have the resources, then transfer learning is the only option, or you go for any online kind of resources. But if we are lucky enough, like in NUST or in our lab, we have we have quite good resources, and of course with the collaboration which we have with international partners, we have the resources. So that made this thing possible for us, that we went for from the very training from the very basics, very basic. But once we are going for commercial kind of things, we should go for the like train the model from the very basic. And transfer learning is one of the things. Like it's kind of old now. You should only go for transfer learning if again your resources are quite limited. The things are that incremental learning, continuous learning, their fine tuning, all these kind of things, because we took the idea from the ImageNet. We have a huge amount of data for OCT, but that was not for glaucoma. That was for retinopathy or for edema kind of thing, because that's most commonly, and in that kind of disease we have more scans in comparison to glaucoma. But with the help of this fine tuning incremental, we are actually finding those glaucoma and other diseases.
Sir, another question, I got my answer, thank you. Another question is, sir, we have only classify different kind of diseases in using retina images. Is it possible to classify that how severe these images, in which stages these diseases are?
Yeah, I was showing the glaucoma slide. In that, we are also highlighting the severity as well. So again, when we are just looking at on the public data set, we are limited with respect to the annotation or with respect to labeling they had, and they generally have that only the grade, only one label, like it glaucoma or AMD or something. But with the help of doctor, again we further annotate the data into different severities, and then once we have that data, we can easily use these models for the severity as well.
Thank you, sir.
And I just, before a question, I just want to mention one thing, like Brigadier Imam Basit from AFIO, he played a vital role in all these kind of systems. Like he's your family member, I think.
My nephew.
Yes.
I didn't know he was into this sort of funny business. And a very interesting talk, and I'm sorry I missed the first few minutes. The Margala Avenue was choked.
Sir.
It took me about 35 minutes to cross from F10 and to cross the park. So I got here late. I apologize for that. But I have a question. You basing all this is basically image processing.
Yes.
And you're taking it to a new level. Based on data collected by different ophthalmologists.
Yes.
Now, many iterations are required. Do you go back and forth, and improve all the time? Is it how it was done?
No, that's kind of a traditional approach. Like back in 2014, when we started that deep learning and these kind of models were not
So
that.
you are saying this is the knowledge?
Yeah.
No, I disagree there.
No, I'm not just saying like this is our knowledge in that sense, like it has all the capability, but we do not have to go back from the very basics, or we do
Not
not
the basics,
need to train it from the scratch. Like
Because
in
every
image.
time a diagnosis is made,
Yeah.
then it's good to have a backup in the sense that look, somebody can confirm this
Yes,
physically.
yeah.
I wouldn't trust machine only. Also, you talked about your patent in South Korea, very nice. Can algorithms be patented?
No, that wasn't the algorithm. That was the gadget which we made for the device. Like if we are putting a gadget. We have a portable gadget which we place with the camera, and
I saw
it
that.
was the complete utility which patented. Like it's not the algorithm. नीचे जाए नीचे और नीचे ये 48
47?
48
48.
so we have like we does have this gadget with us as well, but for the patent at that time we had the idea and we patented this idea along with the complete utility, so it's not just the algorithm.
Right, so let me just ask you, related to this, you have all this gadgetry.
Sir,
Does every ophthalmologist have the same gadgetry also?
right, again, like we do have the IP, but well, that's the commercialization, which is the next step right now. So we have tested that thing, like it works, and it requires the retina. But that's the thing, that's kind of a next step where someone can come in, and we own the IP. So now we are looking for the companies which can come in and they take it to the next step. That's what IP is for.
And lastly, one more comment, nothing to do with reference. And your previous lecture, what was I think of Naveed? Naveed Zaman.
Sir,
Retired now, first met him when he was appointed.
sir,
And there is something that will meet with you and lecture class. Great. Are you an engineer? Signal? No, he said, I'm from infantry. I know how to handle people. I'm glad that this has not happened with you people.
Sir.
To get your work done.
Like, sir, we were lucky enough to have mentors like Sir Shweb and all those kind of scenarios. So we are trying to follow their footsteps. Sir. Sir.
Thank you so much, Dr. Osmanakram, for such a nice talk. I am also thankful to the President, Pakistan Academy of Sciences, General Secretary, Dr. Tasawwur, Pakistan Academy of Sciences, and all the guests, Dr. Sikandar and Sir Yu, and all the students who participated from Quaid-e-Azam University. We have some refreshment for you people, but before going that, we will have a group photo in front of Pakistan Academy. Yeah. Sir. Sir. Okay. So, yeah. Right. Sir. So you can take your tea and then onward move to the bus so it can reach university on time for the departure of other students. So thank you so much. Thank you all. The online audience as well.